Thank you. So yesterday I promised to give you a proof of the Castelnuovo-Iskowski theorem. So decompose a map in a circuit of links. So I will prove this today. We'll just recall some little. So the main result today is this proposition that will serve to prove the theorem of yesterday. So you take a Morey fiber space. Morey fiber space. So in our case, it means Fn to P1 or P2 to a point. Just this. And then now you take a diagram like this. So you start by birational morphism, eta y to x, birational morphism. So just where this is a boost projective, so it's just a sequence of blow up. And then I take a -1 curve. So we'll take a E. So today I will work with -1 curve. What does it mean? E is isomorphic to P1, so it's a closed curve in Y, it's isomorphic to P1, and E square equal to -1. Okay, that's the assumption, and then the result. I will give a diagram. So then there exists. This is the hypothesis. Everything, this is the hypothesis. And then the result is that there is a commutative diagram. So I take X. Y, I have eta, X, B, I go to W, B prime, is also a Morey fiber space. I have in the below compositions of circuits of link and automorphism. Okay, so that's I have this, and what happens? I have a birational morphism there. So everything is birational morphism there, and then this is a blow up of P, and I call it tau, and E tau -1. P, this is a birational morphism, so a sequence of blobs. All my birational morphisms here are between smooth projective surfaces and rational. It will be just a sequence of blobs. Okay, so that's the main proposition. We will prove it. It would be probably almost the whole hour to prove it. And then, as a consequence, we will get the theorem after just a few lines. And but more things. For example, I have a -1 curve. I can contract it. The Castelnuovo criterion for rational surface. I can prove it like this. I can also prove that every minimal surfaces is a Fn with n not 1 or P2. It follows from this also. So I will prove a sequence of results. Okay, for this, that's the proposition. So I will start the proof. But before I start, I will just recall something. So yesterday, I think, or maybe on Tuesday, we discussed that we have, if you have I recall that if you have a morphism, Y blew up P, that's a pi. Then you have a curve there. And you recall that C tilde y pi star of C minus quality in the picard exceptional. Okay, and now what you can take, if you have a curve, you have the curve here. If you have your point, I take Q, a point in E. Then what you know is that the multiplicity of Q of C style is smaller or equal than the multiplicity of P. Okay, so how do you prove this? It's just because you have the result of yesterday that I proved yesterday, but I stated it on Tuesday. If I intersect this, multiply by E, this is -1 times this, so it's MP. Okay. And this is the sum on all points in the bubble space. So Evgeny asked me if I will use the bubble space, not as a set, but in fact I use a lot on what you should do as you have birational morphism, you have some points and you can exchange the points if they are disjunct and otherwise not so. I will use a bit the bubble space. Okay, so bubble space of X, and this is the MQ. So for 1 point, maybe I should not take the same Q. 0. If you have a point there, then here it will count with the multiplicity times 1, so it has to be smaller than this. So that proves that if you have a curve, you have a multiplicity, you blow up, and then you look at the multiplicity on the strict transform, it's smaller or equal. And then, in general, if you have, that's what we will do often. If you have a sequence of blow-ups, and then you have X there, and then C here, and then you can take the strict transform there, and write all the exceptional divisor, and then this would be pi. Then you have pi star of C tilde minus sum of the mi. And what you know, what is the EI is the pullback of the exceptional divisor. Then the multiplicity is the multiplicity here, and then if pi. So if you have a point, and then you have some point which is above, the multiplicity has to be smaller. Okay, so that's the thing that we'll need, and I will try to prove the proposition. Okay, so now I do this with a -1 curve. In fact, the classical version is with the linear system. You take a Baracha map, and then you take the preimage of, for example, you take P2, you take preimage of a line, and you do this. But you can do with -1 curve. You can do with a pencil. I think Stefan told me that he took my proof in his book, and then he added the version with a pencil also. So you can do the proof similar. Okay. Today I do it with -1 curve, and it's sufficient for what I do. Okay, so you have a morphism here. So this is given, the eta is given. So everything at the left is given, and now you want to prove what is at the right. So we will decompose it. So you start by y to x, and then you decompose it. So you write it, x is y0, 1, 2, m. And then you have a sequence of blow-ups. So eta I is the blow up of pi, and pi is in yi minus 1. Okay, and then you can, usually what I do is do like this. I have this curly that I will almost never use, but just it's the pullback. It's the so you blow up a point, you get the preimage. It is a curve which is self-intersection, so isomorphic to P1, so it's a -1 curve. And now you take it back, and I will call it EI. So it's somewhere. So for example, this curly one is there, the second is there, and so on. But then I want to see everything on the top. So I call EI, which is E eta M eta I plus 1. So why it's interesting, it's because now the picker of y, it's eta star the picker of x. Like this, so it's a direct sum, and the EI square is -1, and EI times EJ is 0 if I j, and then they're also orthogonal. Okay, so you have a kind of a basis. If you take a basis of x, it's a modifiable space, so you have picker rank 2 or 1. You have a nice basis on the top, which is which comes from what comes below, and the exception. Yes? Now, yes. I will do this for a long time. So, no, I didn't prove, but I stated here. I use it. But I could assume that it's a sequence of blow-up if you want. In fact, in some sense, it's not really. I think I'm not so sure that I will need it. For the moment, I assume this. So for me, birational morphism is the same as sequence of blow-ups, because I am birational morphism between smooth projective surfaces, and it's the case. But yes, I didn't prove that. I stated. Other questions? Okay, so I have my nice basis. So the EI, you have to just keep in mind, if they are all different in x, then they are really curves. But the PIs is the points. But if it's a point and then a point on the exceptional divisor, this corresponds to things which are not irreducible. The sum of curves with some coefficients. Often the coefficient can be large. But you don't care, just to have this form. And when you have a curve here, the important is that you take the strict transform, you write it like this, with the EI like this, and then the MI are just the multiplicity. That's the only thing you need. Okay, and this you do by induction. Okay, so now we will do the proof. So you have many cases, at least I don't know, remember 5, 6. So the first, I will do first, eta E is a point. So remember, you have -1 curve on the top, and any -1 curve, it has nothing to do with the birational morphism, so it can be contracted, it can be sent to anything. So first, I say it is contracted. Okay, so it means that it's a curve which will contract at some point. So up to exchanging the order, we can assume E is equal to EM. That's the last one. Okay, because what is important now is that if you have a -1 curve contracted, you cannot blow up anything on it. If you blow up something, it will be each of the curve which is here, it's -1 curve somewhere, and when you blow up something on it, it will be -2, -3, -4. So if on the top it's -1, you have blown it up at some point, and then you have done nothing on it. So you could have just say, okay, what I do after, I do it before. That's the main thing, which is a bit like in the bubble space. I blow up some points, I blow up some points after. That's the main thing we do. We blow up at the right, at the left. It's simple. So because it's contracted, I can assume it's the last one, and then you are happy. You just have eta m, which is my tau. So tau is eta m. So you have already the tau, which is eta m. You have the rest, which is the good, and here this is the identity, and w is x. I will just write it phi. Okay. So you do nothing. So this is the easy case. Yeah, good. Maybe tell me if maybe some other people are lost. Yeah. My assumption is there. You have Murray-Fiber space, you have a Berational morphism, and you have a -1 curve, which has nothing to do with the Berational morphism. And now I assume that it's contracted by my Berational morphism. And if it's contracted, then you say, okay, I'm happy. I can contract first the curve and then go down. And here it's just the identity. I've done nothing. Okay? So it will be the very easy case. So if you are lost, like Serge, tell me stuff, because it will be worse after. Huh? Yes? Yes. Case 1. Yeah, to not lose too many people, I will if suppose or assume okay. Now we can assume that eta e is not a point, so it's a curve. Okay, so that's a second case, but there will be many subcases. So now eta e, I will call it e x because it's in my curve inside, is a curve. As the image of a curve by morphism is either a point on the curve, it's irreducible. Okay, now what you have is that e, it's what I wanted to write there. I write it in this basis. So it's eta star of ax minus some and ai ei. 1, 2. These are the multiplicities at ei. So you have a curve downstairs. Upstairs you have a curve which is smooth. You contract. In general, it will be not smooth at all. You will have singularities. And then you will have singularities at the point you have blown up. And then you will call them multiplicity ai. So if it's 2, it's really singular. If it's 1, it just passes through the point, it's smooth. If it's 0, it doesn't pass through the point. Okay? That's what we do always in this topic. Do this, and we will look at the multiplicity, and then we will look at the degree of this. And usually there is Sarkis of degree. I don't really use the classical thing. Okay, and then there are two things we know on this. We know that e square is -1. And then when you do square, this is the intersection there, which is just like in peak x, so it's ex square minus sum of the ai square. And also, you can check with the adjunction formula that you have e times ky, which is -1 because it is isomorphic to P1. So the sum of these two things should be -2. So if you have -1 for one, you have -1 for the other. And then it will be ex times kx plus. That's the two things we will use. And then we will do just calculations with this and a bit of geometry. That's the, I think, the first proof by Castelnuovo was exactly with this. He didn't really write canonical divisor and these things, but he has also all these numbers. Just that he didn't have the -1 curve, it takes the linear system. Okay. So I take a birational morphism from y to x, which is for me a sequence of blowups, and I define the EI like this. They are not reducible. They are not irreducible. Exactly. In general, I mean, it could be that they are irreducible by chance, but in general, they will not be irreducible. Yeah. Me, I like the basis because I like orthogonal basis. That's my. I know that some people take street transform in dimension higher. They take street transform. Me, I don't like this street transform. I don't take street transform. I always take pullback. Dimension 2, I think it's much better. Maybe in dimension 3, you can, think about street transform because you want to see it. But I mean, for the calculation, try to do the calculation with street transform and come back to me afterwards. Huh? Okay. So I just do this because they have orthogonal basis, so that the formula is very simple. Okay, now, just if I have a small case, maybe I should stop the numbering. Maybe two. Allez, I will continue numbering, we'll see. If x is P2, now, if it's P2, because the curve EX is in P2, in a curve in P2, it's self-intersection at least 1. If you have a line, it's 1. If you have a conic, it's 4. It has to be the degree to the square. Okay, so it's not -1. So you have blown up at least 1 point. So M is at least 1. And then we replace. So you have at least 1 point, we just can replace x, which was my y0, with the blow-up of the first point, which is y1. And you can do this because the blow-up of a point of P2, my definition is not maybe an isomorphism, but it's an isomorphism and a isomorphism. So it's okay. And then I can, if I prove it with the first one, I can prove it. I just need a composition of maps which has to be product of automorphism of isomorphism, and then something happens. But then, if the first one is a composition, I can forget the first one, and then I just look at the next one. So I can assume I am only in Fn. We can now assume x is Fn. We have the m, which is the number of blowups. I have the n of the Fn. Okay, now I will write the degree d. D is equal to Ex times F. Fiber. Okay. And this is we have seen it. It's at least 0. Just because it's a fiber, it's 0, and otherwise its intersection with another curve is non-negative. Okay, so you have, let's say 3. If E equal to 0, then it means it's a fiber. Is a fiber. Okay, so now you, yes? Yes, a definition. I define D like this. So I will have a D, a B afterwards, small b, and I have the AI. I will have also epsilon, which come after. You will see. Okay, so D, keep in mind, until the end. That's the degree of the curve in some sense, degree with respect to a fiber. Okay, if it's 0, then it means you have a curve in Fn, intersect with the fiber is 0, but it's a fiber. Okay, so if it's a fiber, now you have a fiber, self-intersection 0, you blow up, and on the top it's a -1 curve. So how many points did you blow up on the curve? One. Good. 2 people answer. Okay, then only one. Exactly one, not only, exactly. Exactly 1 point on Ex. Okay? So, we can exchange the order and choose that it's the first one. And assume is E1. Okay, so you have blown up, you have Fn, you have Ex, which is a fiber, you have blown up, it was eta 1, you have Y1, you have Y. So you have 1 -1 curve there. You have one self-intersection 0, which is Ex, and then you have blown up 1 point. Then you get a -1 curve. Okay, now when you blow up a point on your irreducible surface, the first thing you want to do, you contract the fiber. I mean, you want to do circuits of links, you have no choice. Okay, then I go to F and prime is n plus -1, not at all important. So I go to a irreducible surface, I do a circuit of link, and that's a type 2. Okay, you blow up something, you contract. Okay, and now, instead of looking at this, I will look at this. But now my curve is contracted. My milestone is contracted. Okay? And afterwards, everything what I blow up is not on the green. So it's the same as before. If you blow up something, then you blow up something else. You can first blow up this and then this. So I can blow up all this first, from here, I see everything there, and then do the blow up after. That's exactly what I do here. I have my tau, which is contraction of this green one, and I have the rest. Is my birational morphism. Sequence of blow ups. I just take these ones, and I exchange this and this, basically. And contracts, and I'm done. Okay? Yeah. For me, contraction is just the inverse of a blow up. It's a blow up. Yeah. I have a blow up, so that the exceptional divisor is my curve that I started with. It's exactly what. Yeah, I proved that it exists. Because it's a sequence of blow-ups, and then I just exchange, when I blow up something and something, I can exchange. I don't need anything for this. It's just an exchange. In fact, because it's a curve. Now, this contraction, I proved it yesterday as a circuit of link. So this contraction, I proved it. And the other one is just you exchange. So that's important. I really don't use the fact that any -1 curve can be quadratic. Okay, well, it's not so important if you believe it, so because it's true, but just you don't really assume. Okay. Good. So if d equal to 0, then it's done. Now we will do d for d bigger or than 0, or bigger, it's an integer, so at least 1. And we will do induction on d. Of course, the case d equal to 0 already done. So now if I have 1, if I can always decrease the degree d, I'm happy because I go back to my case of before. Okay, subcase, maybe. Suppose 2ai is bigger than d for some I. So in the classical terms, it's a maximal multiplicity. So for the circuit of links, you have a point whose multiplicity is large with respect to the degree. So here, because I am in conic bundle, it's 2. But in general, it could be 3 for P2. But you will see it's really important. It's really 2 times, it's not something else. So now we can assume I is equal to 1, because I can take the maximal multiplicity to be the first one. If I have a point of multiplicity large, if I have 2 points, one on after another one, the smaller, as I explained before, has multiplicity bigger or equal. So I can take the points which are really in X, and then I can say, okay, this is my first point. Now, when you have a sequence of points to blow up, you have, if they are all in Pn, you can choose on P2 you can choose the order you want. If they are infinitely near, you have to start by the ones which are downstairs in P2 or in Fn. So, but here, this one, I can choose the guy downstairs because I took a maximal multiplicity. Okay, and what you do, but you do the same trick. Same picture. Almost. Okay, so I go to y1, fn, fn prime, circuit of link. Now I have the same picture also as before. Maybe I do the picture because it's not my EX, but I don't know. Before it was my EX. Was this guy, but now I have still a curve, which is my fiber. I blow up my point. I have my 2 - 1 curve, and I contract the blue one here and the yellow here. Yellow. And the curve EX, you should think is like this. The curve which has the multiplicity there, which should be big, would be 1. But okay. And now I blow it up. So with my picture, in my picture, it looks like more multiplicity 2. And then if I blow up this thing, I will pass through there. And now I look at what happens here. For this morphism, now I replace this guy by this guy. And the difference is that before I was finished. But now I'm not finished, so I just have to calculate. So we replace y to fn, which was x, by y to fn prime. Okay, and what you do this, the d doesn't change. Because it's the intersection with the fiber, and this preserves the vibration. So, in fact, if you look at the multiplicity, the intersection of Ex with the fiber, it will be here D. So you have intersection D here, and now you will have intersection which is AI here. So I will write the intersection. In my picture, it will be 2 is 0. So the intersection here would be 2 in my picture, and then 0. So the intersection here will be AI. So I don't write the self-intersection, I run the intersection of Ex with this. And here it will be D minus AI. Because here it's intersection D. So you have a curve which intersects your fiber in D points. You have a blow up of the points. You blow up, the intersection with this is AI, and this is D minus AI, because the pullback of the line is just this plus this. Okay, so the sum of the two intersections makes D. One is AI, the other one is D minus AI. And now I contract. I contract the blue one. So on my picture, I get multiplicity 0. And then the sum, again, will be the D of after, which is the same D. But the multiplicity, so A1, it's a 1. It's a 1. 1. Now A1 is replaced. By D minus AI. Okay, and why then this is important? Of course, because D minus A1 is smaller than A1, exactly because of this. So that's exactly why I chose this condition. In fact, what you do is say, okay, what could I do? If I have a point of multiplicity large, I blow up, I do this. When does it decrease? Okay, assume that it decreases, I do it. In fact, it's the other way we do it. Okay, so if I have some point like this, I blow up and contract. I do not change the D, but I change the AI. The AI decrease. And the whole, of course, the A1, because I have changed, A1 decrease, but the other one, they don't move. Huh? It's the multiplicity of the same curve. So I've just changed one multiplicity, and I make it smaller. Okay. Okay, then if you have another one, you continue, and you continue, and you continue. And so you can do finitely many steps, and you get the new case, which is 4b. So after 4, we have new cases. After finitely, at most m steps, we get for B, I would say, which will be D AI smaller or equal than D for all I. If it's bigger, I can decrease. So at some point, I have this. If I have equality there, when I do this link, I don't change the multiplicity. So it's not so clever to do it. Yes, because you have a curve. The multiplicity is the multiplicity of you have Ex there, strict transform there, and you continue. But for these two, it's the same curve, the same sequence. So the multiplicity of P2 is the point P2 is there, and it's the same point for both morphisms. So it's really equal. How do I define the multiplicity? I take my E, I push it down, and then I take the strict transform at each step. And I look at the multiplicity. Huh? But it's exactly the same curve. For this morphism, I have the same curves on the top. On the bottom, I have two different curves. Here, at the level 0, but level 1 is already the same. So the multiplicity of the first point is different, but the second is the same, third is the same, fourth is the same, and so on. Yeah? 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 Okay, so your picture is this. Like this. Okay, so I blow up this, and I contract, okay? You want? Yeah, what happens? Then you can do the picture if you want. Like this. Then it's completely symmetrical. Yes? The multiplicity AI is the same. Here it's the same in my case, but it's maybe you say high. I didn't take maybe high enough. But for me, it was the same, so it didn't change. But now the P2 will be, the P2 is a point which is there, which is maybe not even on the fiber. It's somewhere else. It's a point I blow up. Here if you want, 2. 10 if you want. Then my picture is not good. It'll be complicated. 10. Ah, no, this is not a point. I have no point there. There is no P2 here. You have only one point there. It's multiplicity 10. The two others are not there. They are there. So if you want to blow up this point, it will be, you have multiplicity 10, so you intersect, and then you have still the 2 points. So the point, if you want to blow up this one, it will be here, P2. It's still there. It didn't change. It's on the second blow up. It's not downstairs. My points are really on all the surfaces on the top, not downstairs. Yeah, it's the same as you can see it as a point downstairs if you want. So if you want to see this point, if you can, multiplicity 1, and then it will be there, this 1. And when I contract, I have a point with multiplicity smaller, but then for the second one, it will be, I don't know, for the picture, 10 minus 5, something like smaller than 10. And then when you blow up, you will still have the same point. But from this point of view, it will be infinity near point, and from this point of view, it's a point downstairs. You're right. Because I replace the multiplicity AI by the other one, and then it's good. I have m multiplicities. I change one. I have maybe m are bad. Each of them become good at one step. No, it's symmetrical. I mean, you can calculate, but the next one, it will be not good. Otherwise, you have to go back. So I don't need to calculate, but it's really the new 2 times this one is always smaller than this. I don't need to calculate because when I do the link, I decrease the multiplicity. So when I come back, I increase the multiplicity. So in fact, you have m steps, m points. Some are good, some are bad, some are large. The large one, I put them down with this technique. And after m steps, they are all small. Okay? I think I will not be able to finish it today. But it's good to ask questions and that everybody tries to understand. I think it's a good thing. Don't worry. It will be good, I will finish tomorrow, but just not good that you have a proof in 2 times. But okay, I will try. Okay, then now you have all the AI are small. That's already something. Some other questions? Okay. Now what I will do. So this is smaller than d for each I. Now I write Ex. Ex. I know that it's d times f is d, so I will write it as d times the section. It's in Fn, huh? Plus b times the fiber. We have proven that yesterday that the pCar is generated by S and F. So it's a multiple of S plus F. We have even say what is some intersection. One is bigger than n times d. This is bigger than d times n. I will use it after, but I will prove it again. Okay, and y is the same d because when you multiply by f, you get d. So it has to be really this d. Okay. So now I write really explicitly these guys so that I have a new number. Huh? So I had already the d before. Now I have the b. Okay, and now I do a new case 5. Suppose that my curve. Okay, I had the case of a fiber, and now it's not a fiber, but it could be a section. And if it's a section, there is one which is special, is the dot S. Okay. Okay, but then it means d equal to 1. It's not equivalent, it's just implication. And b equal to 0. Okay. Then what happens? It's a -1 curve on the top. Ex square is equal to -n, but e square, it's ex square minus sum of the ai square is equal to -1. So this is, of course, smaller or equal than -n square. When you blow up, you decrease the self-intersection. So downstairs was -n, on the top is -1, so n is equal to 1. And ai equal to 0 for all I. Okay? No, you have no -1 curve on P1 cross P1. Ah, yeah, sorry. Okay. Assume that you're right. In my notes, it's this which was written. Okay. Then Ex times is equal to S, and n is bigger than 1, and then I have this. Yeah, you're right. No, the section of 0, it's a general case, so it's good. I don't need to consider it now. It's just the negative section, which is special. Okay, now it's just that I have a -1 curve, but it's in fact the strict transform of the -1 curve. I have done nothing on it. Okay, so I have y to x, which is f1. I have a morphism to p2, which is my eta. No, it's not. It was eta yesterday, but they have 2 eta. So let's take type 3. It's a Sarkisov link of type 3. I contract the -1 curve. I have shown it yesterday that it exists. It's possible, and it's good. And then now this is a sequence of blow-ups. And again, like before, I blow up a point, and now I blow up only points outside. So I exchange. Again, exchange. And you have the tau and the morphism. Okay, then we are happy. Exchange. I do many times the same argument. I blew up something which has nothing, and I can make it. Okay, so this is good. So now I am with the. So this was with when it's negative, and now I will assume that it's non-negative. And then it could be the section 0 in P1 cross P1, or it could be any section in Fn, or something which is not a section, but it cannot be the negative curve in Fn. Okay, so we have done many cases, but I think the more hard is coming now. We'll just do the baby cases. Okay, well, it's not that complicated, but a bit longer. Now we assume, now we are on the, I do my notation. Now we are in 6 Ex times S bigger or equal to 0. And now if you calculate Ex times S, it is equal to minus dn plus b. Okay. B minus dn. That's it. And now, so that implies particular b is bigger or equal than dn. We will need this. Okay, if b equal to 0, that's the case that Stefan mentioned before, you are in P1 times P1. Now you have a if b equal to 0, then b is equal, because this is remember these at least one. Okay, so if b equal to 0, it means n equal to 0. So now you have a curve in P1 cross P1, which is equivalent to a multiple of the section, so it has to be a section of self-intersection 0. Is because it's irreducible. That is a fiber of the other projection. Okay, so what do? We do a link of type 4. A link of type 4. So now type 4, we exchange the two fibrations. So it was a section, now it's a fiber. But it's a case that we did before. And get a fiber. So d equal to 0. Done, finished. Okay. Now, think you have, what, minutes? Okay, now we have the last part. So now we will do EX. So the important thing, I will recall it to tomorrow because I will finish this tomorrow. I have EX, which is ds plus BF, and I will write -1 is equal to x square, which is EX square minus sum of the AI square. -1 is equal to kx times E, maybe 1 is equal to minus kx times V, which is something minus sum of the AI. So now you will have sum of the AI, which is equal to something, sum of the AI square, which is equal to something, and then you play with the two. You get some inequalities, and then you will show that n is equal to 0. So tomorrow I will do this. N equal to 0, or n equal to 1. We can prove with this inequality that it's 0 or 1, and only that afterwards, when you are in 0, but you will do exchange, and when you are in 1, you will go to P2. And you will always decrease the degree. That's what you do. So first, you look at multiplicity which are large. You kill them by doing links of type 2. And then you get at the end where you have no more multiplicity which are large. And then you show that you are n equal to 0 or 1. We had already one case before, but in general, it's also 0, 1. And then the degree will be maybe large, but you do the type 4 or type 1, and you decrease the degree. When you're in F1, you go to P2, and then you blow up again. You go to the next F1, and then you show that you have decreased the degree. Okay, and in fact, that's how the proof works also in dimension 3. You have the circle of link, you don't do with the -1 curve, you do with a linear system, but you have also some multiplicities, you try to kill them by type 2, and then when you have nothing to, when you have only small multiplicity, but you show that you have to do 4 or 1. What you do. But here in dimension 2, it's much easier. Okay. I will show you the end of the proof tomorrow. Sorry for cutting a proof in 2 days, but that's life. There is a question session afterwards. You can also ask them.